The human brain is an impressive organ. Think for a moment what it's capable of doing. Or if you are in the medical field, you may want to consider the catastrophic effects of a brain that doesn't work the way it's supposed to. I don't think anybody would object if I say the human brain is one of the greatest wonders in the universe. It weighs about 3 pounds. Well, there are highly intelligent persons with less than average brain weights, and there are less fortunate people with limited faculties, but with larger than average brains. I'm not saying that the size of the brain doesn't matter. A chimpanzee's brain weighs about a third of the human brain, and the difference does show. Well, the point I like to make is that within certain limits, it is the internal organization of the brain that matters, the way the different neurons relate to each other. Let's take a look at the drawing. A nerve cell, or neuron, is specialized to receive and transmit chemoelectric impulses. The parts of the neuron that receive the impulses from other neurons or from receptors in different parts of the body are usually, but not always, the cell body and the dendrites. Like this. The dendrites, usually several on each neuron, are extensions from the cell body, which gradually taper off and branch in a tree-like fashion close to the cell body. The axon, of which there is usually one to each neuron, transmits the impulses away from the cell body. It varies greatly in length and thickness depending on where it's going and how fast it needs to transmit the impulses. At the very end of the axons are branches with many swellings called boutons, which establish specialized contacts, so-called synapses, with other neurons or with muscles. Synapses, in other words, are sites where the neurons transfer signals which can be either excitatory or inhibitory. Let's take a closer look at the synapse. Here is a synapse, magnified about 20,000 times in the electron microscope. The synapse is characterized foremost by an accumulation of synaptic vesicles in the bouton, which is the presynaptic component of the synapse. The synaptic vesicles contain a specific chemical compound, the neurotransmitter, which is different in different pathways of the brain. When the impulse reaches the bouton, the transmitter is being released from these vesicles into the gap, the synaptic cleft, between the pre- and the postsynaptic membrane. The transmitter diffuses across the gap and triggers a response in the postsynaptic neuron or the muscle cell by reacting with specific molecules or receptors in the postsynaptic membrane. Let's go back to the drawing and take a note of a few and very basic principles of neuronal organization. First, divergence of impulses. A neuron often sends its message to many neurons. Indeed, it's not uncommon for a neuron to project to more than one place by the aid of long branches, so-called axon collaterals. Second, convergence. A neuron usually receives impulses from many sources. Look here, different pathways converging on this neuron. And they may use different transmitters, represented here by different colors. Like that. It is in the specific arrangements of these neuronal circuits and in the way in which they are being used that one must look for the correlation of brain power. Let's think for a moment. Here are 3 or 4 neurons. Imagine millions or even billions of neurons, and many of them establishing hundreds or maybe thousands of synaptic contacts with other neurons. That's the brain, and the complexity is mind-boggling. The elucidation of these neuronal circuits with anatomical, physiological, and pharmacological techniques represents, at least for many, one of the greatest challenges of mankind. Already, some of the most debilitating disorders, like Parkinson's disease, some forms of epilepsy, Alzheimer's disease, schizophrenia, and some of the other major psychoses have, at least to some extent, been correlated with specific changes in the brain. And literally thousands of neuroscientists are working with great expectations and hope of someday finding a cure for the major nervous and mental disorders. By using a combination of light and electron microscopic techniques, it's now possible to trace in detail a neuronal circuits, let's say from A through B to C. And in addition, determine the transmitters involved. Such tracing in itself will not explain how the brain works, or what it is that doesn't work in a patient with a brain disorder. However, the tracing of pathways and the identification of specific circuits in the brain is a necessary prerequisite for such understanding. But before we can even start to trace connections and study specific pathways in the brain, we must learn about its gross anatomical organization. To this end, we will inspect the brain in detail and dissect it to see what's hidden in its interior, using just a few tools. A brain dissection is an obvious first step to learn about the structure of the brain, and it is a step that every health-related student should be prepared to take. Assume you're taking care of a patient that has a certain set of neurological symptoms, and the very first question that arises is the following: where in the brain is the lesion located? Is it located in the hemisphere, in the cerebellum, or maybe in the brainstem? These are the structures that we will take a closer look at. As you'll quickly discover when you start to cut through the brain, some areas have a gray color, other areas have a whitish color. Those parts of the brain that contains aggregations of nerve cell bodies, like this, embedded in a network of fine delicate fibers, have a gray color. That's the gray substance. Other parts contain bundles of nerve fibers, many of which are surrounded by a lipid-rich myelin sheath, which gives these parts a white, glistening color. That's the white substance. There is a very characteristic distribution of gray and white substance in various parts of the brain. For instance, there is an accumulation of gray substance on the surface of the brain called cortex. And there are large areas of gray substance in its interior, which we refer to collectively as subcortical nuclei. Accumulations of gray substance in the peripheral nervous system is referred to as ganglia. The white substance is formed by the various fiber tracts of the brain and by the nerves in the peripheral nervous system. When the brain is taken out from the skull, it is usually surrounded by some of its coverings, and some of the brain vessels are usually also well preserved. Therefore, we'll take a look at some important aspects of the brain membranes, and we'll discuss the blood supply, which is of great clinical relevance. There are 3 membranes around the brain: dura mater, arachnoid, and pia mater. The dura mater is closely attached to the inner surface of the skull, and most of it is therefore left in the skull when the brain is taken out of the skull. Feel how tough and fibrous the dura mater is. All of these membranes have protective functions, and they also have some very specialized functions that we will discuss. Maybe you remember some of the arrangements of these brain membranes. Let's cut the frontal section through the brain like this. Here it is. The dura is white, and it is closely attached to the inner surface of the skull. Two large sheets of dura, the falx cerebri and the tentorium cerebelli, divide the skull cavity into three communicating compartments: the two supratentorial compartments and the infratentorial compartment. The cerebral hemispheres are located here in the supratentorial compartments, and the brainstem and the cerebellum are located in the infratentorial compartment, like that. Falx cerebri is suspended vertically between the two cerebral hemispheres, and the tentorium cerebelli forms a tent-like partition between the cerebral hemispheres and the cerebellum. The tentorium has a large opening in its anterior part called the tentorial notch, through which the upper part of the brainstem connects with the cerebral hemispheres. The dural venous sinuses are formed where the dural folds attach to the skull. A venous sinus is in effect an endothelium-lined space between two layers of dura, and the sinus's function as a drainage system for the venous blood. Here is the superior sagittal sinus in the midline, and the blood will eventually reach the transverse sinus and other large sinuses on the base of the brain before it gets into the internal jugular vein and back to the heart. How does the venous blood get into the sinus? Look here. This is an enlargement of a cross-section through the superior sagittal sinus. The skull is black, as on the other picture. Inside the skull is the yellow dura. The blue space between the two layers of dura is the venous sinus filled with blood. A vein comes from the dorsolateral surface of the brain, and it simply makes its way right through an opening in the dural membrane into the sinus. Here's another vein that bridges the gap between the brain and the dura. Let's go to the specimen. Here they are, the superficial cerebral veins, here, draining the hemisphere and disappearing here into the superior sagittal sinus. Well, let's make sure there is a sinus here in the midline. I have already cut open the sinus with a pair of scissors, and I'd like for you to look into the sinus here. Look. Here it is, with rather large holes, openings for the veins, and openings to the lateral venous lacuna that is located laterally here. The characteristic feature of these veins, namely the fact that they bridge the gap from the surface of the brain to the rather inelastic dura, make them especially vulnerable in the sense that they may easily tear in head injuries, be there a car accident, a knockout blow by a boxer, or even a trivial head trauma in an elderly person. If that happens, blood is gradually accumulating between the brain surface here and the dura, with sometimes disastrous consequences. This is referred to as a subdural hematoma. Let's see what happens if the blood or the hematoma isn't evacuated. If the bleeding doesn't stop, the pressure increases in the supratentorial compartment, and some of the brain tissue in this compartment tries to escape into areas with less resistance or with better possibilities for expansion. In this case, it is often part of the temporal lobe, known as the parahippocampal gyrus, and the uncus of the parahippocampal gyrus that herniates out through the tentorial notch, which is the natural opening in the tentorial membrane. So this is, in other words, a real herniation. And we refer to it as a transtentorial herniation or an uncal herniation. Another place where brain herniations sometimes occur is at the level of the foramen of magnum. An expansive lesion in the infratentorial compartment, let's say a brain tumor, may increase the pressure in this compartment to such an extent that some parts of the cerebellum, known as the tonsils, herniates out through the foramen magnum. That is the tonsillar herniation. You have probably realized by now that brain herniations are very serious complications of a brain lesion. It doesn't necessarily have to be a subdural hematoma. It can be any type of bleeding, or a tumor, or an infection. And it is usually accompanied by an alarming deterioration of consciousness. In the case of the transtentorial herniation, the third cranial nerve, the oculomotor nerve, is usually involved at an early stage. Why is that? Let's take a look. Look here on the ventral side of the brain. Here's the brainstem and the cerebellum located in the infratentorial compartments, whereas the main part of the brain with the two cerebral hemispheres are located in the supratentorial compartments. I'll let this piece of cardboard simulate the tentorium cerebelli. As you can see here, there is a large oval opening in the anterior part of the tentorium. That's where the brainstem connects with the two cerebral hemispheres. We'll insert the tentorium here in its position between the cerebellum and the cerebral hemispheres. Do it carefully so I don't chip away the brain tissue. Here it is, in its natural position like this, but we will look here on the base of the brain. Here is the large artery on the ventral surface of the brainstem. That's the basilar artery, and it divides up at this level into the two posterior cerebral arteries, one on each side. And on the left side here is the large oculomotor nerve hooking around the posterior cerebral artery here on its way to the orbit. Well, in the level here, at the level of the tentorial notch, some very interesting topographic relations. Look, here is the medial surface of the temporal lobe. This is the parahippocampal gyrus, and the hook-shaped part here is the uncus. And these are the parts that protrude out over the edge of the tentorial opening in an uncal herniation. And the protruding tissue literally presses here on the oculomotor nerve, or the oculomotor nerve is caught by the posterior cerebral artery and stretched when the brainstem is dislocated downward. Deterioration of consciousness and ocular signs are main symptoms of an uncal herniation. And the cardinal signs of a third nerve lesion are oculomotor paralysis and dilation of the pupil, usually on the side of the herniation. The other two membranes are much thinner than the dura. They are the arachnoid, painted black in this drawing, and the pia mater with a pinkish color. They are in many places connected to each other by fine tissue strands or trabeculae, and they are therefore often regarded as an entity, the pia arachnoid. But between the two membranes is, nevertheless, a very important space referred to as the subarachnoid space, which contains the cerebrospinal fluid, CSF, which, among other things, serves as an additional protection for the brain, a water cushion, so to speak. In spite of the fact that the arachnoid and the pia mater are closely related, there is an important difference between the two membranes. Whereas the pia mater closely follows the surface of the brain, the arachnoid follows the inside of the dura. In other words, the arachnoid bridges over the irregularities of the brain surface, and where the irregularities are pronounced, large cavities are formed. These are the so-called subarachnoid cisterns, which, in other words, are widened parts of the subarachnoid space. Tissue from the arachnoid, so-called arachnoid granulations, collections of microscopic arachnoid villi, protrude into the sinus, or usually into lateral extensions of the sinus here. It is through the arachnoid granulations that most of the cerebrospinal fluid is absorbed into the venous system. Well, let's see if we can detect some of the arachnoid granulations here. We have already opened the superior sagittal sinus, and there are a few blood vessels coming in here, and maybe here some granulations. But usually what one has to do is to look in the lateral extensions of the superior sagittal sinus. Let's see. Here in the front, here's a hole. We can go in here, open the venous lacuna here, the lateral side, and, well, there are a few granulations here, but I think we have to go to another brain to see some good granulations. Here, as you can see, are some magnificent granulations attached still to the pia arachnoid when the dura was removed from the brain. And as you can see, these arachnoid granulations are located here on both sides of the superior sagittal sinus that's running here in the midline. Now, let's see if we can get an idea about the subarachnoid space. Unfortunately, when the brain is taken out from the skull, the cerebrospinal fluid escapes and the subarachnoid space collapses. So you have to use your own imagination to get a feeling for what the subarachnoid space is like and how the cerebrospinal fluid flows from the base of the brain in the subarachnoid space up towards the superior sagittal sinus. Well, if we are lucky, we should be able to recognize some of the large cisterns around the brain. One is the cerebellomedullary cistern, cisterna magna. And as the name indicates, this cistern is located in the angle between the cerebellum and the medulla oblongata. Well, in this case, unfortunately, the membrane is ruptured, but you know, we can reconstruct the cavity, the cisterna magna, like this. This is what it looks like, a large cavity. And if we destroy this membrane, the arachnoid membrane, well, we lift it aside, we should be able even to recognize one of the holes here, the median foramen of Majordi, through which the cerebrospinal fluid escapes from the interior of the brain into the subarachnoid space, here represented by the cisterna magna. Let's try to get a better view of the aperture of Majordi. We'll turn the brain around, upside down, and we will part here the medulla oblongata from the cerebellum. Take a close look here, and you will be able to see the choroid plexus in the roof of the fourth ventricle. The choroid plexus is a structure that produces the cerebrospinal fluid. Well, the choroid plexus in the fourth ventricle produces only part of the cerebrospinal fluid. Most of it is produced in the choroid plexa in the large lateral ventricles of the cerebral hemisphere. Well, now we'll see if we can look for the other two holes in the fourth ventricle. The best way to look for the lateral apertures of Luschka, one on each side of the brain, is to look here, in the angle between the cerebellum and the medulla oblongata. Look for a piece of cauliflower, a cauliflowerette as it were. Well, here it is. Look. And we will take a probe and see if we can probe the lateral aperture. Here it goes. Yeah, there is the hole. When the cerebrospinal fluid has escaped through these three holes into the cisterna magna, it distributes to some other large cisterns here on the base of the brain, and finally through the rest of the subarachnoid space up towards the superior sagittal sinus, where it disappears through the arachnoid granulations. Let's see if we can look for some of the other large cisterns. This is the interpeduncular cistern. You can still see the membrane bridging over here. And further forward, around the optic chiasm, is the chiasmatic cistern. Here, unfortunately, the arachnoid is disrupted. Well, there is another cistern that is here on the lateral surface, completely collapsed. That's the cistern of the lateral fossa, which bridges over the lateral fissure at this level. There is another cistern called the lumbar cistern that most medical personnel are familiar with. That's the cistern you aim for with your lumbar puncture needle when you want to take out some cerebrospinal fluid for diagnostic purposes. And as you know, that cistern is located below the spinal cord.